Let's play a little bit with time and degrees of a cam-crank relationship here. This is Ronnie's capture he made of his Chrysler LHS with a jump timing belt, and we'll use that for our demonstration. We don't need this thing here. It's just going to be in the way. Let's get rid of it. So we need to know not necessarily how fast this engine is revving, but what we need to know is how long does it take it to go one cycle or one revolution. On this car, it has a sync signal. This one here has 5, so we can go from the beginning of that one to the beginning of this, and that's one engine RPM, which is 890 RPM. And if you have a crank sensor that doesn't have a sync, you may know that it has 3 groups for every engine revolution. It may be an analog signal that has a bunch. You don't necessarily know exactly how many with no sync whatsoever. But the cam will have a sync. As in this one, it has 1, 2, 3, 1, 3, 2. So if we take these and you go to the beginning of this one here, it's a little tough to get to. And you take the next one and you go to this one here, so you have the whole pattern. We got 437 RPM, but that's an engine cycle, which is 2 revolutions. So you have to times that by 2 to get your RPM. 720 degrees between these two, and it takes 137 milliseconds. So you can use this measurement or the first one. And I don't like either one because my eyes aren't good enough for this. I usually like to use something with compression, as I said before. So we'll go back to that, and we'll get a compression one coming up here. So there it is. And again, we don't need this. We'll get rid of that. So this capture was made a couple days later, so the RPM is not going to be exactly the same. So if you put a cursor at the peak of each one, that's an engine cycle. That's 720 degrees. So once again, you have to multiply it by 2, and we get 819 RPM if you multiply this by 2 for 720 degrees, which really doesn't mean a lot because that's not the number we want. This is the number right here that we're after. 146.5 milliseconds, that's the number we're concerned with. So what we're after is to see how far this cam is retarded from where it should be. So we're going to figure out in degrees how far it is. So what we need to do is figure out how many degrees there is for every millisecond of time is about the easiest way I know how to do it. Normally I use a calculator on a desk and a pad of paper, and I write all my notes down just in case I have to go back, and then I have already an idea of the numbers I'm going to use. But for this we'll use a calculator. Bring it up here. So we're going to divide this by itself and 720 degrees by this. So we take 720 degrees, which is between these two cursors here and here, and we divide that by 146.5 milliseconds, and we have 4.92, we could say, degrees for every 1 millisecond in time. Now I would just write that down on the pad of paper, but we'll leave it up on the calculator here. So if we're going to find out now how far retarded this is, we just need to zoom in on that space. We don't need this anymore. We can zoom in. Let's just zoom in on this much. So if we put the cursors up here, put one here, where'd the other one go? And one here. Whoop. We can lock those cursors, and then when you move them, it's like moving this group of cams into here. So the ideal position is to have them right in the very middle, right about there. So now we know that we want to move the back part of this cam sensor to this position. And we want to know, like, how many milliseconds is that? Right? So now this is our position right here. We can unlock that, and we can measure the time between this leg, and we want to go over here. And it's 8.29 milliseconds is how far we're going to move that. So when you bring up our calculator, this is the degrees per millisecond times 8.29 milliseconds is how far we moved it, is 40.74 degrees. This is how far this camshaft here is retarded from where its optimum position is. And that's how I normally do it. I find it to be the fastest way and the easiest way to do that little job. Now, if we zoom back in again, you don't necessarily have to put these here and lock them. You can simply say, well, I got this part, and for it to not code, I just have to clear this. All I have to do is be in here somewhere. And that's okay. Then you bring your other cursor up here, and you put it here and say, well, that's all I have to move it. But if you're going to go through all this work, you might as well put this one here and lock it and say, let's put it in the absolute ideal position and dead center that sucker. And if you want, you can do the same, because it only takes a minute with this. The only thing with this is I take the widest group, because when you take a smaller group, it's easy to put this in here, but you don't want to put it in dead center because that's not the right spot. If you take a wider group, this is the biggest group. So if you put that in a dead center, then you know that these other ones will be okay. That's why I always use the biggest ones when I measure this on a Kreiser, because then I never run into a problem with did I move it far enough or did I not. Now, if you don't have a compression one, and we'll go back to the one we had before, here it is. It's coming up slowly. And there it is. So there's, get rid of this piece of poop again. So there's no compression for the peaks. So let's do it just using what we know. Here's from here to here is one engine revolution. Let's zoom in on that. So that's 360 degrees. So we'll do the same thing with 360 degrees. Where's my little calculator? There's my calculator. Let's clear that up. So we have 360 degrees divided by 67.4 milliseconds is 5.34 degrees per millisecond. Remember, this is a different capture from a different day. So we'll just save that number, and now we can do the same thing as we did before. Let's make it easier on my old eyes. You put this here, and you put this here. Lock them cursors. Get that at the ideal position. Just because it's a Kreiser, you don't necessarily have to do this with every car. This is just the way I happen to like doing it. So we're moving this part of the cam sensor to this position, 6.81 milliseconds. So this is per millisecond of degrees times 6.81 equals pretty much the same as before. 36.4 degrees retarded from where it would be optimum. And you'll get different numbers, because maybe one day you're going to move it, and you could be off just a hair here. Well, you're going to get a bit of a different result in the end. But as long as you have these two cursors between here somewhere, you're not going to ever code. It just gives you a basic idea. Yeah, this cam is retarded, and it's retarded a bunch. So let's go back to where we were. Get rid of this thing. So you can see, even without a compression, you can still pick either an engine cycle or an engine revolution. You can very easily figure out how many degrees different things are. Once you know the amount of degrees per millisecond, you can use the same number to say, well, I still got them locked. How many degrees wide is this tooth? Or how many degrees wide is this group of teeth? You can use that for anything. Now, if you have a long capture, you got to realize that the times will change from the beginning to the end when the engine revs up and down slightly by maybe 50 RPM or something like that. You maybe can't use that same number for the whole capture, but you can use it for anything very close to where you got the initial number of how many degrees 1 millisecond is. Now, also, in a couple of the tutorials, probably more than I realize, they have touched on this. Brian's used the same method to measure degrees, had the calculator the same and everything. It's not like I'm the guy that thought this all up. I'm just a peon that happens to use it. And I believe in the tutorials, he does touch on the same thing in both of these, the compression waveform overlay tool and the waveform viewer that we get for free for being Pico members. And Rod from Australia made those, and he's kind enough to give them to us. And when they explain how to use them, they do show you how to use the calculator to figure out how many degrees different parts of the waveform are apart. Now, I didn't think of this all myself. I don't even know if I used it much before I seen it on Auto Nerds, but I think I did back in the days when I used to play with Mick. But if you look in the section in Auto Nerds where it's the private section and they have all the tutorials, these two little tutorials here with Rod's software that he give us. When Brian explains how to use the software, he does show how to use this method for calculating degrees of different parts of waveforms, cam, crank, or compression, whatever you're looking at. They can use this overlay tool for sure, and I believe the latest version of the compression waveform viewer also has a cursor in there. What I don't like about those is they'll only give you how many degrees it is from the peaks. So you put, I'm not going to bring up those two tools right here, but you bring up your cursors for the peaks of the compression, and the third cursor tells you how many degrees it is from your very first cursor. So if I'm doing a cam-crank relationship, that doesn't do me a whole lot of good when I want to pick a certain small part out of the middle between two cursors. I can't use those tools. But Brian does show you how to use the calculator to figure out degrees in a waveform. So I hope that's a little bit about what somebody wanted to know. And if it's not, just ask me a question and I'll see if I can think up some kind of a bullshit answer to give you and pacify you, because it'll probably be some bullshit involved. Have a good day.